record, do this all over. All right, so unless I'm crazy, there's literally just 8 people in this room and only 7 of you are students. So none of the boys wanted to wake up. That's cool. Okay, so I want to talk a little bit about Fluorine, because Fluorine is a very special lady. She has some interesting reactivity that is related to what we're doing today. And oh, there's our boy. Andy has joined. Yay, Andy. So today's notes, we're going to go over the middle 2 pages on electronegativity and ionization energy. And electronegativity is like super important in terms of what it all means for what elements end up doing. And then ionization energy kind of goes into stuff for next week as well. And then we'll again do a refresh of what is due when, and that's it. All right, so fluorine. Fluorine is special. I have often made jokes about fluorine that you may not understand why I'm joking about fluorine, but you will. Fluorine has the strongest amount of attraction for any of the elements, with the exception of helium and neon, but helium and neon both have full electron shells, since they all the way fill their shell. So helium and neon don't need anything. So while they have a lot of attraction, helium and neon don't do anything with their attraction. Fluorine, however, does lots of things with all of its very strong attraction. So fluorine is highly, highly reactive. It is very, very dangerous. I often refer to fluorine as an element that will eat your face off. It will liquidate your lungs. It is really, really nasty, and you do not want it anywhere near you in any way, shape, or form. And that's talking about the element fluorine, because then people are like, but there's fluoride in my toothpaste, and that's not bad, is it? And no, it's not, because fluoride is not fluorine. Fluoride already has its electron. So you need the fluoride in your toothpaste, but fluorine, if it was around you, would eat your face off. So that's super, super bad. Fluorine is able to force other elements to do things that they actually do not ever want to do. And this had to, the fact that fluorine could do this actually kind of changed our definition of what the noble gases are. Because up until the 1960s, it was assumed that noble gases do not make compounds. And that is not actually true. Several of the noble gases do make compounds, but only with fluorine. So the first element this was seen with was xenon. Xenon can make 3 different compounds with fluorine, because fluorine basically has so much attraction that it can attract and force, we'll say the word force, xenon to make bonds with some of its outer valence electrons. And this actually happens under fairly normal conditions. And then under some weirder conditions, fluorine can also do this with krypton. And under some extremely weird conditions, it's actually been found in the last 20 years or so that oxygen can do this as well. Because what we're going to find is, out of the elements with that really strong Coulombic attraction, right behind fluorine is sitting oxygen. So these guys have some like very special abilities, all because of that high amount of Coulombic attraction that they have. So our noble gases, it's not that they don't react, because some of them can, but what we do say is the definition of a noble gas is not that it doesn't react, it's that it has a full energy shell. So that definition ended up kind of having to change in the 60s because of fluorine and her special abilities. So we're going to go to the notes today. These are the same as last week. We're going to cover, like I said, the electronegativity and ionization energy. So let me switch over. Somewhere, there it is. Okay. So we are going to start with electronegativity. And this is a super, super long word that up until very recently, Microsoft Word did not even recognize as a word and always gave me the red squiggly line under electronegativity, which, since I'm a bad speller, it always made me really nervous. But I was like, no, that's a word. That's how you spell it. But I will often abbreviate it as an E-in because that is much easier to write than electronegativity, instead of writing that over and over again. But electronegativity is the ability of a bonded atom to attract shared electrons. So this is slightly different because this only exists inside a compound. All right, so this is measured inside a compound. So this kind of little diagram over here is just a little demonstration of what it is we're talking about. So if you can imagine if these were some a fluorine and a hydrogen, that it's the ability for the nucleus of fluorine or whatever element to attract that bonded, that shared electron. So it's not attracting its own electron. It's not taking somebody's electron as it passes near. It's you're in a bond and I'm pulling. So this is basically leads to unequal sharing. Because we can imagine that these two electrons, well, they're kind of there in the middle, but they're actually constantly playing a tug of war, and one side is tugging harder than the other. It's kind of like what I described. You know how a Kit Kat comes with 4 bars, and you could share a Kit Kat and break it in half and keep 2 for yourself and give 2 to somebody else, and that's sharing. But you could also share a Kit Kat by breaking off 1 piece and keeping 3 for yourself and giving 1 away. So that's unequal sharing. Still sharing. So if your parent tells you you have to share your chocolate, and you're like, well, I don't have to share it equally. You didn't say that. Follow the letter of the law. Okay, so electronegativity is a way essentially to measure attraction itself. So it is a measurement of attraction, which makes it easier. So if we look on this diagram here, this is what we refer to as like a heat map. And this heat map of electronegativity shows you who's got really high electronegativity and who's got really low electronegativity. So which element has the largest electronegativity value? Who is the brightest of the reds?
Fluorine.
Fluorine. When you're spelling fluorine, make sure you're spelling fluorine and not flourine. U before the O in fluorine. Okay, so the largest electronegativity value is fluorine, by far, 4.0. This is an arbitrary scale because it's just made by comparison. So fluorine is our most electronegative element. And if you will see, the next most electronegative element is oxygen. And then the 2 after that are nitrogen and chlorine. So all things that are very small in size and that have a high amount of nuclear charge. So our smallest electronegativity values all the way down here on the opposite side with francium. And again, this tracks with everything we've learned so far, because down here by francium, we have low coulombic attraction, because I'm a big fat element with very low nuclear charge, as opposed to up here where fluorine is, where I have very high coulombic attraction. All right, so with all that being said, the interesting thing to note is we have these elements that do not have any values listed, as well as all of these radioactive guys at the bottom, because we don't really care about them. But those ones that in general don't have any electronegativity values, those are our noble gases. And while some of them actually technically do have values, in general, we just don't list them at all because basically noble gases don't form any kind of bonds. So they don't form bonds, and that's part literally of the definition for electronegativity. So if you don't make a bond and you don't share electrons, you can't technically have electronegativity. You have to be able to make a bond to have electronegativity. So if these guys don't make bonds, then they can't have electronegativity. And in general, they don't normally make bonds because they have full valence shells. They don't need to make bonds. They have everything they need. All right. The full valence shell means that, with the exception of helium with its 2, everybody's already got 8. We make bonds to get 8. They already got 8. They are not bothered. So that's why you're not going to see any values here for those guys, not on the Linus-Pauling scale, which is what this is. So if we try and explain why, well, our explanation for why we see the trends we do in electronegativity are the exact same for the why our Coulombic attraction is high up at the top right and low down at the bottom left. Because again, electronegativity is just another way to state attraction. So from left to right across a period, the electronegativity increases because the nuclear charge increases. You're plugging all the valence electrons into the exact same energy level. So your attraction for bonded electrons is going to increase. Right? If we're increasing the charge while the distance stays the same, you're clearly going to increase attraction. So that's what we see left to right. And that is a very, very obvious trend left to right, that there is a big change there from left to right in all of these periods, more so than we see with atomic radius. So there's a very large change left to right in the attraction here in the electronegativity. But as we're going top to bottom, well, it's very obvious that we see a decrease in values. And we have a decrease in values because our valence electrons keep entering a new larger and larger shell, which is farther away. And if they are farther away from the nucleus, that attraction is going to decrease. So again, there's not really any difference in these two explanations versus what we wrote in the Coulombic attraction notes. Those are essentially the exact same thing. So if anybody needs or wants to take a picture of that, go for it. And otherwise, I will scooch up a little in a second. And since we've started, I've seen Ioannabelle, Kamaya, Sania, Davi, all enter. Maggie too, so. Okay, I'm moving. It's not a whole lot, but it's easier to write. Okay, so our other trend is ionization energy. And we're going to think about ionization energy in 2 ways. One way today and then another way on Tuesday. So ionization energy, well, it's got energy in there. So energy is required to do things. And ionization refers to ions. So it's the energy to make ions is essentially what it is without even thinking any more about it. But it's the energy required to remove electrons. And so what we are making is we are making cations. So we're talking about the energy required to make a cation. Now, you already know which side of the periodic table likes making cations, likes to be a cation, the left or the right?
Left.
Left. The left-hand side already likes to make cations. So are we going to imagine that the left-hand side has high values for this or low values for this?
Low.
Low, because to make an ion requires energy. So if you make ions easily, then it shouldn't require very much energy. So for this one, you kind of have to think about there's a multiple chain of logic that you have to go through when you're thinking about ionization energy. How hard is it to pull off an electron? So therefore, how much energy should it take? And go through that whole fact. So ionization energies are all positive values because, whoops, that is not what I meant to do. Because energy is going in, all right? It's going in to be able to pull off the electron. And that should make sense because there is attraction there, all right? So think of this as like pulling a magnet off your fridge. Let's see here, which makes sense because an attraction between the electron and nucleus is being broken. We have to break the attraction between the electron and the nucleus to pull off an electron. So this is like you actually physically pulling a magnet off of your fridge. It requires energy for you to do that because the magnet and the fridge have an attraction. So it requires energy to break an attraction. So that should make sense. And if energy is going in, and if it is positive, is that exo or endothermic?
Endothermic?
It is endo. Because endo means in, and it is positive. Okay. So the amount of energy required is directly proportional to how attracted the electron is. So a direct relationship means more attraction is going to give us more energy required. Right? It's like one of those things is if you have, you know, those tiny, tiny little super strong magnets, it's like this tiny thing. You don't think it's very hard, but then you actually have to put a lot of energy into fully pulling it off. Okay, so finish getting all that down, and then I will switch pages. Okay. So this picture is a little bit different from the others I've been showing you because it's not showing you the periodic table. It's showing you a graph of everything. But the thing you can tell very easily by looking at this is if you look at the highest values for all of these things, the top of all of these peaks, well, what elements are those?
Noble gases.
Those are all the noble gases. Again, the noble gases have a full energy shell. They have all 8. They do not want to lose an electron. They're like, do not take my stuff. Don't touch it. Leave it alone. And I will have super high electronegativities. But on the flip side, the elements with the absolute lowest ionization energies are what group?
One.
All right, that's group 1. So these are our group 1 alkali metals. And what do we know about our group 1 alkali metals in terms of ions?
They like forming 1+ cations.
Yep. So they like losing an electron. And so while it does require energy to become a cation, for these elements, it does not require very much. So if you kind of think of it that way, it makes it a little bit easier to think about what's going on with your elements here. So let's answer some of these questions then. So the element that seems to have the highest or the largest ionization energy is which one?
Helium.
Helium. All right. And that should make sense because helium is the smallest and actually has the highest amount of Coulombic attraction. All right. So, but again, that means helium is up at the top and the right-hand side. And the element that seems to have the smallest it's hard to tell. I think it's cesium on here. You will find that you would expect francium to be right here, except francium's radioactive, so we don't do tests with it. So our smallest one is cesium, which would also make sense because it is in the area of lowest attraction. So our simple explanations here. So from left to right across a period, so looking at helium, neon, argon, krypton, xenon, or no, sorry, looking at like sodium, magnesium, aluminum, blah, blah, blah. All right, so left to right going that way. That's our left to right, sorry. So if we look left to right across a period, the ionization energy is doing what? Increasing or decreasing?
Increasing.
It is increasing. And it's increasing because the nuclear charge is doing what?
Increasing.
Also increasing.
Wait, I'm confused. How is it increasing?
How is, which one?
So you said from left to right, so like from helium to the...
No. That's what I accidentally did at first because this is not showing the periodic table. So sodium is on the left-hand side of your periodic table. Argon is on the right-hand side. So from left to right, what is it doing?
Oh, okay.
Yeah, I messed that up too. And it's my graph. So, all right. So the nuclear charge is increasing while our valence electrons are entering the same shell. So the attraction, if both of those two things are increasing, well, that means the attraction is increasing. And increasing attraction means it requires more or less energy to pull off an electron.
More.
Okay. So that's your left to right explanation. This is your top to bottom explanation. Top to bottom. Now let's look top to bottom. All right, so what's happening as we go from top down to bottom here? Ionization energy is doing what?
Decreasing.
Decreasing, yeah. This is what we wanted to say the first time, Kai. So our valence electrons are entering this larger shells, which is farther away. So what's happening to my attraction if I've got things farther and farther away?
Decreasing.
Decreasing. And if I have decreased attraction, more or less energy is required? Less. So you can think of it as helium as being like one of those super strong neodymium or neodymium magnets that requires lots and lots of energy to yank off. And like cesium being one of those really, really cheap delivery pizza magnets that's practically like a piece of paper that just falls off at the slightest provocation. So those are your two basic explanations. That's the important stuff for you to get down. But I am going to go over, this time, some exceptions to the rules, which I don't normally talk about exceptions in here, but it's very obvious what the exceptions are here or where they are because they follow a repeating pattern. So I'm going to scroll up just a little. Okay. So there are some blips, and the blips occur in fairly regular amounts. And I want to highlight where they are. So we have that blip, right? It weirdly goes back down. And then we also have this blip that also weirdly goes back down. All right, these are not smooth trending upward lines. And then we see that this blip is the same, it happens here. And this blip is the same, it happens here. And if we want to repeat on, well, it happens here and it happens here. And then it kind of happens less as we keep going. So there's definitely some spots where this thing happens, and we have to figure out kind of why. So it's difficult to see with this diagram because it doesn't include all of the element symbols, but those blips occur in group 13 and they occur in group 16. So these have abnormally low ionization energies. They are lower than expected. And lower than expected means, do I have more or less attraction if my ionization energy is lower than expected?
Less.
Less. So that means there is something that is giving me a weirdly smaller amount of attraction here for those elements. And we haven't really talked about that, although it does exist for all of these trends, but it's most prominent with the ionization energy. So first off, let's talk about the group 13. So my group 13 elements, that is boron, aluminum, gallium, etc. All right, that's what we're talking about. So the group 13 elements all have electron configurations that end with a full s2 and then a single electron in p1. So for boron, it would be 1s2, 2s2, 2p1. For aluminum, it would be 1s2, 2s2, 2p6, 3s2, and then 3p1. So that's what I'm talking about. They all have this. They all end that way. So there's something about that that is giving us slightly less attraction. So this p right here, that last p electron experiences a small amount of what we refer to as shielding. Remember, and shielding is that notion of canceling out some of the nuclear charge. So we have some shielding from this guy. All right, so it's that full S2 acts like an extra little piece of cotton around the nucleus, providing some buffering. So that shielding is going to just slightly decrease the attraction. And again, if we have less attraction, that means it is easier to remove and less energy is required, and you get a lower ionization energy. Okay, so it is these guys decrease the attraction felt by that P1 electron. It's not a lot, it's a little, but it's enough. All right, so that explains the group 13 elements. The other group in here is the group 16 elements. So for group 16, this is oxygen, sulfur, selenium, etc. These guys, if I do oxygen, it would be 1s2, 2s2, 2p4. Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. So we're talking about this section. All right. So if I have 4 electrons in P, this is where it is helpful to still remember that orbital diagrams, those arrow things. So P4, if I've got, all right, 3 orbitals in P, so I've got 3 P orbitals here, and my 4 electrons are going to go 1, 2, 3, 4. This right here is what makes that blip. And here's why. So these individual single electrons, well, they're happy. But the paired electrons, when you shove 2 electrons next to each other, what are they going to do to each other?
Repel.
They will repel. They say, I do not want to be next to you. That is not my favorite place to be. So we are going to push against each other. And if they are repelling against each other, that is the exact opposite of attraction. So repelling is going to decrease attraction. So anytime you have repulsion, it decreases attraction. So if you have decreased attraction, so less attraction means easier to remove, less energy required, and a lower ionization energy. Okay, so it is these paired electrons. So paired electrons increases repulsion, decreases attraction. So that explains that little blip there. So let me scoot that up just a little to make it slightly easier for people to take pictures, because that's the end of these notes. So take a minute, get that down, and then I'll switch back over to the slide deck. Ow. Okay, so due by the end of the week, Edpuzzle video 34, which about half the class is already done. It's basically me going over this exact same stuff. The exit ticket on the next screen. The concept builder. The first level dealt with atomic radius. The second level is, I think, electronegativity, and the third level is ionization energy. So you should be able to easily do all of those. And the concept builder is basically just asking you, like, between a pair, pick which one has the lowest value, or pick which one has the highest value for this thing. So essentially, the very top portion of each of our notes, where we talk about what the trend is and where the biggest and the smallest values are, that's what you need to be able to do the concept builder. So practice that, get your trophies, take a picture, throw it on Google Classroom. Then the thing that is graded for accuracy this week is the Google Doc and Google Classroom. So for that guy, some of it is just multiple choice. And then for anything where I say you have to write stuff out, it is these explanations in the notes or what you want to pattern your answer after. So kind of like from top to bottom down a group. Something decreases because the distance increases, so you have decreased attraction, like that sort of thing. So that activity actually should be pretty easy if you have your notes in front of you. And then there are some free response questions on Flipgrid this week. So again, the extra credit, it's anything you get right, I give you extra credit points. So you don't have to get the whole thing right to get all those points. If you answer one portion of the free response question correctly, I'll give you partial credit on the extra credit. So I think only once or twice have I actually had somebody get all of a free response question correct, which makes sense because they're AP level. And that's it. So there is your exit ticket. I'll type it into the chat. Review. Bam. And that's it. So
Thomas
for
Baskin.
people who are doing the AP class, I will see you guys tomorrow for a little informational session. And otherwise, the next time I see all of you guys, I will be 43 instead of 40.